Hello, here I am, Jeffrey Fox. I'm the instructor for the Big Data Applications and Analytics course, and we're in the Health and Medical Informatics section, and we're at Lesson 5. Lesson 5 is described here. It's actually this part of the course. I'm getting pretty short summaries, and it's a set of a presentation I found relatively recent, just a few months ago, about a cloud-based medical system from Potsdam. And when I started looking at this particular unit, maybe almost 2 years ago now, there was rather little on the web about cloud-based medicine. Now there's getting a little more, and this particular discussion here was reasonably impressive in my opinion. Of course, you can't tell so much from what they say, how much is real and things like that, but I thought it was quite thoughtfully done, and I remember I could not find such discussions 2 years ago. So this says the field is maturing. People are really doing cloud-based medicine. And so this is the Hasso-Plattner Institute in Potsdam, which is where the talk comes from. It's on SlideShare. August 27th was the date it was put there. And so this tells you the challenge. You have genomic data, proteomic data, hospital information systems. Notice this is 50 gigabytes, and that's 15 petabytes. And here we have actually not so much terabytes of raw proteomic data. Cancer patient records, not so much. PubMed database, 23 million articles. Bet you haven't read all of those. Here we have modern instruments, scans of single organs in a second, giving you 10 gigabytes of data. Large images are a feature of modern medical instrument. Here we have insurance data, prescription data, clinical trials, and then we have real-time analysis, which is going to, that we actually had a little section on just on telemedicine. And of course, the idea of telemedicine, take the real-time census from a hospital, from a patient sitting over in Timbuktu. And here we have our doctor in the very best hospital in, I don't know, Boston or something. And that real-time data is feeding information to the doctor, who has all this repositories of existing information available to the doctor, and she is making great decisions and bringing the wisdom of the Boston medical centers to Timbuktu. But Timbuktu is just a proxy for people in the not in more rural, remote areas. We did Ogdensburg in the Adirondacks in our telemedicine section. That's what we were working on 20 years ago, rather unsuccessfully. Well, we were actually successful. We just were not able to jumpstart an activity. The demos we did were quite convincing, and actually, even with the low-speed internet of those days, you could do quite a lot. We used to do actually distance education. I did more distance education in the 1990s than I do now, and we were doing that with 10 to a maximum of 100 kilobits per second links between Syracuse, where I was, and universities around the country, where I taught, for instance, the first Java classes to some students. So here we have comments on they're doing in-memory database technology. Remember, Gartner classifies in-memory databases as critical, and that allows these real-time analyses, because if everything is in memory, you can do things instantly. And here are some nice, pretty things we're doing. Row and store data, map reduce, compressing the data in a nifty, clean fashion, real-time replication to get things good access, reducing the speeding things up by putting things in integers. We do that to save data today. SQL, elegant software, text retrieval to analyze those 23 million articles, We have object relational mappings in the, we did that in the cloud section. We had these tools from Apache to do that. We have data being transported on UPS trucks to move them into the clouds and so on. Everything is partitioned to support parallel computing. And we're doing everything dynamically on the fly with elastic clouds. We're doing historical data. Say here we're parallelizing it. And obviously this fellow doesn't like disks. I recommend, obviously there's lots of technology, caching and in-memory, what we have here in-memory databases to minimize the need to keep going to disks, which is slow. All right, so here's the cloud platform to analyze genomes. And we have genome metadata, research publications misspelled, genome data. We have models and pipelines and drugs and their interactions. That's usually done with semantic databases. So that's what's called linked data, the semantic databases, often using Sparkle queries and RDF and things like that, OWL ontologies. And we have here, this is just this is a scatter of sort of concepts. Here we have the real-time analysis. I pointed out we want to combine here the archival data with the real-time data to be able to align the real-time data with the existing data to do the best possible analysis. Here we have data on what drugs do. Here we analyze cohorts of patients, and we have some sort of portal of medical knowledge, wisdom. So that's that cloud platform in a rather qualitative fashion. Here we have the real-time processing events. We already discussed sensor data from monitoring the patient in the intensive care unit. We have the quantifying self-type sensor devices measuring in real-time calories and pulse and heart and all sorts of things so that we can tell when you're going to get an order soon when you're running around the track saying, stop, you're about to have a heart attack. We just detected it, and people are meant to lie down and stop and save themselves. And of course, it all uses machine learning to detect these events, outliers, match events which they see on a given patient with events on other patients where we know the outcome. And this is done at, 10 events per second, which is meant to be sufficient for ICU use. If you build all these typical Storm Apache systems for small events, it's trivial with a single core actually to do around 1,000, well, let's say 250 events per second, but you can get much higher rates than that in a very easy fashion by just having multiple cores. I mean, parallelism, because when you have when you're gathering data, the whole point about the cloud is the cloud can initiate all sorts of brokers which are receiving the data and capturing it and labeling it and making it available to other people, and that's naturally parallel. This is not totally, it's what I call modestly parallel. It is not totally pleasingly parallel because there's some connection between those events and their labeling, but still it's quite easy to build a parallel version with rather loose synchronization. Here we have drug side effects as one active part of this cloud system, which again comes from looking at accumulated data, to look at correlations that are which have been discovered, or your data itself reports, and then you integrate in your own prescription data and report the side effects. So it allows you to in real time update this data, and this can all be done with the doctor and this cloud-based system working together to combine real-time data from sensors and from the patient themselves with the accumulated wisdom sitting in these repositories. So here we have this medical knowledge cockpit, which is commonly called a portal, which is the user interface, and it allows you to actually access this magnificent system. Presumably here you have a patient with various windows with properties of the patient, and You're allowed to browse that, search for related information, and so on. And again, they keep stressing how, because they do everything in memory, they're fast. Of course, you don't have to do in memory to do it. You just have to do it in memory to make it faster. So something which doesn't happen so often, it doesn't actually matter if it's in memory or not, because you will just be able to fetch it off disk and do it. Disk isn't slow compared to people. It's just slow compared to memory. And computers do things at 10 to the 9th times per second, and when the people only work at a little bit a second. So we know a typical human reaction from frames per second needed for quality video, that's 30 frames per second. So people do something in a 30th of a second possibly. Here we have Jane Doe, and we have this cockpit. We already pointed out that this would give you the information relevant for the studying this person's health. This poor lady has lung cancer. And you have electronic medical records, and you can search for related disease, literature, biomarker information. Here you have processing the sequence data, the DNA data. These are just various formats for DNS data. And obviously have security issues to keep privacy individual users. And you can store everything you did, have a history. And you're allowed to, presumably, this is sort of unusually sophisticated. I'm not certain it matters today about fair use, that each department gets an equal amount of use. If you have enough cloud computing, you should be able to give everybody all the use they want. So annotation is very important, and I gather this got a European Life Science Award. So this, of course, is what you're doing. You're doing a modeling, and you have a runtime, and you run pipelines, orchestrated pipelines. We did that in the cloud computing software section. And here's our last slide from this particular talk from this. I don't know of an equivalently sophisticated system in the US. I don't think there's anything here which is not known and understood broadly, but it's very difficult to implement anything in the US because you don't have access to the data, and the conservative people in charge of the data don't have either the resources or motivation to do it. So anyway, so this is telling you what, again, summarizing, we can look at clinical trials and medical experts. We can start the therapy as soon as possible because everything is done digitally. We can do appropriate diagnostics. We can look at the drug-related issues. We can, of course, this is a critical broad-based thing. You're scanning for similar things. This is a recommender engine. Given you're a patient, you want to find other patients that are near you, and you can look at what happened to those patients, what drugs they took, what side effects there were, and things like that. So this, remember, we did in sports, we looked at pitchers which are near other pitchers for a particular batter. So we want to take patients and look for patients near each other, a giant recommender engine. And of course, for some things we can do free text searches to see what's known in the literature, because there's so many papers. No one person has any deep knowledge of any one of, other than the very few papers, nowhere near a significant fraction of the 23 million that exist. So that's the end of this cloud big data system, which I think is a reasonably good summary of what we ought to be doing. They had, unfortunately, no graphs. We used this system and we saved the lives of 552 people, or we cut the cost of healthcare, or we reduced medical errors. There were no. And also we discovered diseases which had not been discovered by doctors. There's nothing like that here. So I would say that's the only weakness of this report. As a concept, it's very well thought out, and it appears to me it ought to be highly successful. But that's just based on my ideas that what ought to be possible.